Hi everybody. Today we are going to study liquids, but not everything about liquids. You already know about Archimedes principle. You already know about pressure in the liquid, right? All that is a phenomena that is in the bulk of this liquid. Today we are going to focus on the surface of the liquid. What happens at the surface? Well, you may say, what is special about the surface? Isn't the same thing happening at the surface? No. Something very different happens at the surface. We are going to talk about that, which is the principle of surface tension. So, why surface tension? Why is there tension only at the surface? Why do we specially take it out? Because the rest of the liquid actually has pressure, whereas at the surface you have tension. Pressure is compression, basically push, whereas at the surface there is a pull. Let's try to understand the difference. Now, generally you know that intermolecular forces between two molecules, two atoms, right? You know that the force is repulsive if you are very close, and you know it's a little bit attractive once you start moving out. In fact, you may have seen a graph of this type. You probably saw this for energy, but there's a similar graph for force. This is force versus distance. So suppose I kept one atom here and the second atom was there. The force is negative, which basically means the force is in this direction. How much? Given by this. Right? This is the magnitude. Negative basically tells you it is in this direction. You know that is the positive direction. This is the negative direction. So the force is negative, as in this is kept fixed. This fellow is at this distance. You will see so much force. Small force. Very close to zero. As the molecule or atom comes closer and closer, you see a large negative force. And then if it comes closer, the force keeps decreasing. This point is the equilibrium position. So generally, if I keep two molecules or two atoms, they will remain at the equilibrium position. That is the distance at which they stop. Okay, this is the point where the force has become zero. See, the force has become zero there. If you push them too close, that is, they're getting much closer than this. Once they are here, the force increases rapidly. There is a huge force. Can you see that? Once the atom is here, the force has become very large. If it got even closer, the force increases dramatically. So obviously you cannot get two atoms that close to each other. But if you got them a little further away, it is an attractive force. Basically, if the atoms were like this, they will pull. But if the atoms were like this, they will push. I hope everybody understands this. When the distance between atoms increases beyond this, they pull. When the distance decreases, they will push. This is the equilibrium position. So I hope you understand that. Let us now think about what is happening here in the bulk. Basically, if you take the bulk of the liquid like water, the molecules are compressed a little bit. Why are they compressed a little bit? Because of the weight. So if I take this liquid, not on the surface, somewhere here, this molecule and this molecule are very close to each other, little bit closer than this. Not too close, just a slight amount, because even a little bit of closeness ensures that there is a lot of repulsive force, because you see that it's rising like that. So small compression will generate a huge repulsive force. So this fellow is pushing that fellow and that fellow is pushing this fellow. Then this fellow is pushing this fellow is pushing that fellow. In your book and in most books, they say that there is attractive forces. I don't think that's right, because you're talking about pressure. You know that you talk about pressure. Pressure is because something is compressed, so it is pushing back. So these molecules are pushing those molecules, right? This one is pushing that. Similarly, if I had a molecule here that is pushing this, this fellow is pushing that. This molecule is pushing this fellow, that molecule is pushing that. So if you see, the diagram looks almost the same, like in all directions there are forces, but they are all push forces. This molecule is not pulling this fellow, is pushing this fellow. Okay, they are all repulsive forces, they are pushing. Why? Because this guy is in close, slightly closer than the equilibrium position. All the molecules are close to each other. Why are they close to each other? Because of gravity, they get compressed. If you had let them be, let's say they would have been at the equilibrium distance, all this weight has to be borne, right? So it's getting compressed slightly. Though we say water is incompressible, there's a slight amount, very, very slight amount. It doesn't change the density or volume much, but it does increase the force between them. This force, which is a pushing force, there is a push here, there is a push here. This force leads to the concept of pressure. So we say water or any liquid in the bulk has pressure, and the pressure basically pushes the liquid. which is why if I took a surface here, you feel a push force, right, from this side, and similarly a push force from that side. Now let us think about the surface. Now if you take the surface, which you have molecules like this at the surface, the molecule that is just below this is pushing this fellow up, right? There is a push. So here, this molecule is pushing it up. This molecule is getting pushed down, is getting pushed this way, this way, this way. So this is not going to go anywhere. But that molecule is only getting pushed up. It is also getting pushed this way and getting pushed this way. But those two will cancel. But how will this cancel? It won't cancel. So it will actually start going up. So this molecule will go up like this. Just think of it this way. Suppose I had these three molecules. From the bottom, if I push this molecule, this is going up. But this distance is now larger. So earlier what would be like this distance is now like that. But can you think of this? This is the hypotenuse. Clearly this is bigger than this distance. How much bigger? Well, it used to be compression, and because it did this, this has now gone beyond the equilibrium and it is now extended. Therefore, there is an attraction. See, here it used to push each other. This fellow was pushing that fellow was pushing this fellow. But now these two are large enough, the distance has increased more than the equilibrium. So now they are pulling each other. This guy is pulling that fellow, this guy is pulling that fellow. This fellow is pulling that fellow is pulling this fellow. Notice the character of the force has changed. In the bulk, the character of the force is a push force. At the surface, suddenly it has become a pull force. I want you to understand that it's a significant pull force, big pull force, okay? So, and not just that. What is interesting is that if you look at this force and this force, think of this force, let's call it F and F. And let's call this F1. If you think of this angle is theta. F cos theta plus F cos theta, 2F cos theta has to compensate for F1. 2F cos theta is F1, right? So F must be F1 by 2 cos theta. Now F1 is that pressure force, which is okay, but this theta is almost 90 degrees. It's not like this is bent so much. This is a small angle. It's like slight angle, that's all. If this, for this small angle, I mean small angle as in it is almost 90, slightly less than 90. So cos theta is close to cos 90. But what is cos 90? Cos 90 is 0. So that means F1 by a very small number. Because it's F1 by a very small number, the force with which you are pulling, this is called the surface tension force, because it acts at the surface, is much, much larger than F1. That is, pressure forces, if they are, let us say, 10 units, I'm just coming up with some number, surface tension forces are like 100 units. Why? Because this is a very small number. So you are dividing it by something like 0.1. So that means it's becoming 10 times larger. So surface tension forces are very significant because they are huge forces. Why are they huge forces? Because the stretch force has to compensate. It's not directly compensating. Its component will have to compensate. This component will cancel, this component has to compensate, but this is a very small component. Just imagine, like I've drawn it at a very bad angle. So just imagine that it was like this, right? Only this component will help. To compensate for this component, you need such a large force to fight against this much force. This force is so small, whereas this force is so large. This is the surface tension force, only acts at the surface. So why is there a surface tension force? The surface molecules are stretched, because you see this guy gets pushed, it's like this. Similarly, this also gets pushed. So overall, because of the pressure from the bottom, usually surfaces turn out to be like this. They are stretched. They are like that. If it is possible to be like this, they will basically stretch out because there is a force acting like this from the bottom. This is the pressure force. And then there are tension forces like this between these molecules. Now all of these are stretched. So they are pulling like this. Okay, I want you to think of it that way. This molecule, that molecule, that molecule, like that. They are basically pulling each other. This is pulling that, that is pulling this. And you can see that this pull produces a force in this direction that fights the force from inside. So the surface is like a stretched membrane. Tension means pulling. Compression, pressure, right? It's a compression, pushing. So pressure is a pushing force. Only at the surface you have a pulling force. That's why this phenomena is called surface tension. You don't have the tension inside, you only have it at the surface. For every surface you will get surface tension. And the reason it's an important phenomena is because surface tension tends to be a very large force, right? Usually, if I draw this a little bit more carefully, let me draw it again for you to see. So if I look at this graph, usually pressure is acting at this level. So this is the pressure forces, surface tension is usually here. So the pressure forces, you're talking about this magnitude, whereas for surface tension, you're talking about that magnitude. So I hope the first difference is clear to you, why surface tension occurs. Surface tension is because molecules are pulling each other. So let us quickly look at what you would have learnt from your book, okay, or what is written in most books. So most books would say that in the bulk also, this fellow is getting pulled. This molecule is pulling that fellow, this molecule is pulling, and all these forces cancel. And they say that at the top also you are getting pulled, and similarly this is pulling that, and that is pulling this. So it looks like surface tension is a force, which is a pulling force, and inside also there is pulling force. But that doesn't tell you why it is tension at the top and not tension inside. So this diagram, while this is what is generally referred to in most books, it's not correct. The bulk of the liquid, the molecules are not attracting each other, they are repelling each other. Okay, so what is happening is that this fellow is pushing that fellow, which I won't mark, but this fellow is pushing that. Notice, here it is a pull, that is a push. This is also a push, that is also a push, that is also a push. Net force is zero, we both agree, right? The book also says that, this also says that. But I am saying that they are pushing and the pushes cancel. The book and many places, many teachers may also say that there is a pull and the pull cancels, but that's not correct. There is a change in the nature of the force. Here it is a push force. Okay, so this is the correct thing. This is a push force. Even here, this molecule is pushing that molecule. This molecule is pushing that molecule. But these two molecules are pulling each other. There is pull here, whereas this is push. Okay? Everywhere in the bulk, it is a push, except at the surface where it is a pull. Now let us try to understand. So I'm going to look at the top surface and I'm going to draw it like this. So I take the top surface like this of the liquid and I'm going to draw it on the board this way. Okay? So if this is the surface of the liquid, there are molecules here, right? And there are molecules there. It's a stretched membrane, but we can think of the stretched membrane as almost flat. There is a small curvature like that because it's getting pushed up, but we don't need to worry about that right now. Okay, so but at this point we'll think of it as a flat surface. So think of it as a flat surface. Let us look at the row of molecules. So if you look at the row of molecules, and it continues, I mean it's all directions, it continues. This molecule is getting pulled by this molecule. It's a pull now, only for the surface. It's a push everywhere else. Only at the surface, it is a pull. But then there is also a pull like this. Then similarly, this molecule is pulling that fellow. This molecule is pulling that fellow. There is also a pull in this direction, which I won't draw right now. But you must also imagine there are pulls that way. So if I look at this row of molecules is getting pulled this way and getting pulled that way. Similarly, this row of molecules will get pulled this way and this way. Right? So overall, what is the net force on that row of molecules? Zero, because there's a pull this way and a pull that way. Actually, if you think about it, it won't be so clearly zero. There will be a small force this way and that way. It has to compensate for this force. So there is a cos theta, which is a very small amount that I've already told you. So F 2F cos theta, if this is theta, must be equal to F1. So you know that it won't exactly cancel, but we will ignore that. We'll assume that is almost straight, just for understanding it. Okay, imagine it's a flat surface. Later we will come back to this because this is important. We will study the fact that there are curved surfaces, then what happens? That we will study a little bit later. At this point, I want you to just look at this. This force cancels out this force. So net force on that row, 0. But is it 0 because this force was 5 and that was 5? Or is it 0 because that force is 50 and this is 50? Big difference, no? Whether my two hands are getting pulled, net force on me is 0. But is it getting pulled with 100 newtons and 100 newtons? Or 1000 newtons and 1000 newtons? If two friends pull, I can still manage. But if two elephants pull me, net force is 0, but my hands will come off, right? So it doesn't matter what is the pull. Net pull, 0. But what is this side's pull? Well, if one intermolecular force was small f, this is f, let us assume they are all equal. And if there are n molecules, the force with which you are getting pulled that way, f, is n times f. But how many molecules are there per unit length? So suppose I say that there are, let us say, x molecules per meter. Suppose we say that. That means in 1 meter, there are how many molecules? There are x molecules. That means the force will be x times f, right? The force per unit length will be x times f. But x is a constant because you know how many molecules are there per unit length. It's hopefully fixed, right? For each material, like for example, if it is water, you will know that there are so many molecules per 1 meter. If you have like ethanol, you will have a different number. You may have different numbers. Similarly, f is also a different number. But if you look at water, water will have, let us say, 10 to the power of, let us say, 18 molecules per meter, okay? Or 10 to the power of, let's say, 12 molecules per meter. Then that into the force per molecule is going to give me the force per unit length. This we call sigma. Understood? For every 1 meter, let's say this was 1 meter, you would get a force of sigma because 1 meter will tell you how many molecules, each molecule have f. So there are f times x times f. So this is going to be sigma. So now, suppose I had a length which was L. Let us say this was 1 meter, L meters, right? For each there is a f or sigma, right? The force is sigma, sigma, sigma. So for L meters, what is the force? L into sigma. So we write force is sigma times L. Force per unit length is sigma. I want you to think about this carefully. I am calling this force. People usually call this surface tension. The sigma is called surface tension of that liquid. Okay. So usually tension itself is force, but surface tension is not force because it is force per molecule. But if I now add up all these molecules, I don't know how many molecules are there. So if I had, let us say, 2 times the length, like 2 meters, for first meter there will be a force, the second meter again there will be the same force. So you will get 2 times the force. So in general for L meters you will get sigma times L. So what is sigma? Sigma is the force per unit length. That basically means if I picked a surface like this, and by the way this was a surface I picked this way, right? I could have taken the list of molecules like this. There are molecules here which are pulling these guys. So if I took a length L like this, there will be a force in this direction perpendicular to that line that I have picked. It's an arbitrary line because you can pick a line and you can say there are molecules on that line and the other molecules are pulling. It's intermolecular force. They are pulling in this direction perpendicular to the side like the length I have taken. How much force? Length times sigma. But is it only in this direction? No, it's also in that direction. What is the net force on that line? 0. But we don't care about net force. We are asking the net force is 0, but is it 0 because it's 5 minus 5, 0, or is it 50 minus 50, 0? So that 5 minus 5 or 50 minus 50, that is the tension. Okay. So the surface tension tells you that this force, right, is sigma, the surface tension times L. And similarly that side also there is a force sigma times L. Net force on that line is of course 0. That's why it's an equilibrium. So I hope this is clear. So surface tension force is sigma times L. If you take water, for water, sigma of water, it has been calculated, measured, it is 0.07 newtons per meter. So surface tension of water is 0.07 newtons per meter, 0.075, okay, sometimes you can use that as approximate value, 0.07507, I think it's 0.72 for pure water, but it also will change a little bit based on temperature, because the number of molecules may change, okay, because it may expand a little bit. So you see that X will change, therefore surface tension will change. But we will talk about surface tension of water as being almost close to 0.07 newtons per meter, a very important value to remember. But if I put soap in water, what happens is that soap molecules interact with water and reduce this intermolecular force. And because of that, for soap solution or soap water, soap solution, sigma of, I'll call it soapy, right, is much less. It is 0.03 newtons per meter. Okay, so soap solution, the surface tension is much, much lower. If you look at mercury, it's amazing. The surface tension is huge. It's 0.46, like way above what you have for water. But we won't worry too much about that. Generally, for each material, you will have its own, each liquid, you have a different surface tension value. Most questions, the surface tension value will be given to you. For water, please remember the surface tension is 0.07. Soap solution, it is 0.03, which is why we say when you add soap to water, the soap solution is formed and therefore surface tension decreases. So what does that mean? That means when I had this big bulge which was holding things up, if I add soap, immediately it will dissolve, and therefore basically it will, the surface tension, it won't dissolve, the soap will dissolve, and as soon as it dissolves, that big bag that we had is going to collapse, because you can't hold that kind of, it's not pulling as much, so it can't hold such a large bag of water. You can see that by adding a little bit of soap. So I'm going to show you that as an experiment. Okay, so first what I'm going to do is I'm going to first create a big bulge like this, and then I will add, I have here a little bit of soap, and as soon as I touch it, you can see that it immediately dissolves and becomes smaller, right? So this tells you that soapy solution or soap solution has a much smaller surface tension. Let us now think about what happens when I try to take an object out of water. Okay, so I'm going to show you that here. You can think of a needle like this. And when this needle is trying to come, let's imagine that this was the surface of water, and if I'm trying to pull this needle, the needle just doesn't come out. The needle has a layer of water here on top and like that. So when I'm pulling the needle up, I'm actually lifting the water because the water is stuck to itself. So the water forms a layer. I'll show you like this. So for example, if I'm trying to lift this needle, the water will form a layer like this. This is the needle. And at some point, of course, this surface will break and it will fall. It's a nice thing to see. I'm going to show it to you here. Okay, so if I look at this beaker, I have water and I have this small frame. So if I look at this frame, I'm going to basically lift this frame. As I'm lifting, you will see that when it comes to the surface, there is a small stretch in the water. Okay, so let us see. I'm going to lift this up. Can you see? Can you see that? It is actually lifted up and then falls. So what is happening is that the water, which was like that, is on top. So it basically lifts up like this and then comes back down. So that's what you're seeing when you're seeing this lift. Like a small film of water, basically, it's trying to lift it up. Can you see that? I'm going to lift this. Yeah. So you can see that there is a small lift and then it falls down, right? Because that is the point where the surface of water broke. The surface of water likes to stick with the surface of water. That is important. So when I'm trying to lift something up, it is sticking with it. It forms a film around it. And as I lift it up, at some point this breaks and it falls down. Okay, that is something that we will use a lot. And we are also going to study a little bit of film, particularly with soap water. So let us look at some idea of what is the meaning of a soap film. So we understood what is meant by the surface of water. Very same idea, very same principle, but with soap films there are some interesting things that we can probably look at. So let us quickly look at a couple of nice experiments with soap films. So now let us look at a small nice experiment which is basically dealing with the idea of surface tension. So if you see, I have here a copper ring with a small thread like this. So I'll draw it. So this is the copper ring and here is that thread which is like that. Okay. So what I'm going to do is I'm going to dip this in soap solution. So it will form a film. It will form a film here and it will form a film there. I can break this film or I can break that film. Okay. So if I break this film, right now what is going to happen is there is a force this way and there is a force that way, because this surface is pulling it like this and the inner surface is pulling it like this. Same way here there is a force this way and a force like that. And this is a flexible thread, so obviously depending on the forces it will either move in or move out. Suppose I break the inner surface. Okay, I can just touch with a small earbud like this. Suppose I touch it and I break the inner surface, there will only be an outer force. So this fellow is going to basically expand. It's going to become a big sized object. On the other hand, if I look at this force and this force, this force and this force, this is a film and that's the film, right? Suppose I break this film, that means this force will go away. And this will pull it in and it will become thin like this. So shall we see this experiment? A very nice and simple experiment. So I'm going to just take this. Okay, so here is my thread. Watch. What I'm going to do is I'm going to first, let's just make this a little bit more rounded like that. And let's put it into the soap solution. So I'm putting it into the soap solution and I'm going to lift it out. So you can see that it has formed a film. There is a film there and there is a film here. I'm going to poke this inner film. So I'm going to break it. The moment I break it, you will see that it will expand a little bit. Ready, steady, go. Can you see that? It's a small expansion. I'll show that again. So in fact, let's make this a little smaller so you can see the effect better. So I'm going to break it and you can see how it expands. So did you see it expand? Okay. If I now break the outer film, nothing much is going to happen because the inner is also broken. But what is interesting is what happens when you break the outer film instead of breaking the inner film. Let's see that. Can you see that it's getting compressed? Because the inner film is still there. So it's pulling it in. So basically here, once I've broken the outer film, the inner film pulls it in, so it becomes smaller. Whereas when I break the inner film, the outer film pulls it out, so it is becoming larger. So basically, this is the idea of surface tension. The surface molecules are pulling. They are pulling there. They are also pulling here. So you break that. If you break that, then this is going to basically dominate. So it's going to come closer like here. And if you break this, then those are going to dominate. So therefore, it's getting pulled out. So I hope that is clear. Very simple, nice experiment using the concept of surface tension. So far, we were looking at single surfaces, right? When you take water, liquid or something like liquid, you look at one surface for liquid. Now I'm going to talk about soap films. So for example, here there is soap water and I'm going to take this frame and there is a soap film here. I'll just blow so that you can see it. Yes, you can see that frame. So if I look at this carefully and I try to draw it, this is what is going to happen. So I have this frame and there is a film there, right? But this film is not one surface. What is this film? This film is actually a layer of water. So if I look at it this way, if you see it this way, this is the water layer. But this water layer has one surface, so this is surface 1. And this side is surface 2. There are two surfaces and there is water trapped in between them. This way, this is surface 1, that is this part, and then this side will be surface 2. So that means you have the back side is surface 2. So if you take a soap film, there are two surfaces that you have to deal with. This is water layer, but that is also a surface, this is also a surface. Now, what will happen if I basically blow on the soap film and so that it becomes like a bubble? Let us look at that carefully. So here I have a soap film. Okay, I am going to pull it. So you can see that the bubble got formed. Let us see if I can pull it and also catch it. Ready, steady, go. Okay, so I have caught it here. So that way you can understand what is the case. Notice that after that bubble, one side broke, there is still a film here. See this. Right? So let us just draw this. A soap bubble is nothing but this soap film that has kind of got blown up that way. So if, for example, this was the frame that kind of pushed it, the soap bubble is not one single surface. It is actually soap water here and one surface inside and one surface outside. So there is an inner surface and there is an outer surface for a soap bubble. and you need to basically consider both of them. Remember, surface tension forces act on the surface, but now there are two surfaces. So when you look at this, if you want to go deep into the molecular level, then you see that these are surface molecules of the soap, and these are the inner molecules. And this thickness, right now it may look like, oh my god, this is like really thin. Yes, it's how many millimeters? Like maybe it's a 0.1 millimeter thickness, right? Or 0.01 millimeter thickness. But in terms of atomic ranges, this is like huge number of atoms. So this may be probably like 100 million atoms thick. So you're talking about a really thick layer from atomic perspective. So this is the surface, this is the surface, this is the bulk. Okay, so there won't be surface tension here, but there will be surface tension forces acting on both surfaces. So whenever we deal with something like this, which is a film, soap film, remember you're talking about two surfaces. When you're talking about a soap bubble, you're talking about two surfaces. Okay, and with soap bubbles, and for example, if I just take a general soap bubble like that, okay, so let me try to blow up one soap bubble. So if I took that soap bubble, this soap bubble has an inner surface and there is air inside, and has an outer surface. Again, there is air outside. Okay, now if you take that frame, now you can see that there is only one film. Whereas earlier this frame was connected to this side one film and that side one film. So generally one film basically itself means two surfaces. Earlier when there was a film here and a film there, it means four surfaces connected to that copper wire. So that's something that you should generally be careful about. And when we solve problems, we will see that if I make a cut on a soap surface, this part is going to pull this up. Similarly, this part is going to pull that up. Because there are two surfaces, you'll have to worry about two forces, not just one F, but two Fs. Now, when we get to problems, we'll look at some of these. And in general, do remember for problem solving, force for each surface is sigma times the length that you are considering for that length on that surface. Okay, so all along the surface you can take a length, and wherever you take that length, there is a force on that length which is equal to sigma times L. Sigma for soap water is much smaller, 0.03, and for general water, regular water, it is 0.07 newtons per meter. Okay,